right. So, welcome back from the kind of long weekend, and then the extended break. I know that didn't impact our class at all, but I hope that some of y'all got to stay put and relax and enjoy a snow day. Hope it didn't undermine any of your plans or anything like that. Um, so a couple of things that I wanted to say. First of all, I'm going to share my screen. And that is because we are getting into organic chemistry today. This is a bit of material where we've got some good poll questions. But before we get into any of that, I want to say a couple of things. Currently, you've got two activities up on Canvas. One of them's a word search, and one of them is a crossword puzzle. And then you've got three quizzes all up on Canvas. These are all due Sunday, the today's the 22nd, so that would be the 26th at 11 p.m. I've gone through and made the adjustments for extended time. Should anyone have contacted me with ODS paperwork, I've added that time. The quizzes, you have 15 minutes each and um, two attempts on them. So take notes, grab screenshots, do whatever you need to do when it comes to answering those quiz questions. Um, then I know that I mentioned this previously, and this is really, I guess, more for the folks who are not here. Um, but we have poll questions, Zoom poll questions, which they are not going to be evaluated based on, if you got it right or wrong. It's participation. I want you to answer them. Um, should you miss class, there will be discussion prompts added to our Canvas site. And the discussion will just be like a prompt that says, class 12225, do this, write three questions about this and write two questions about this. It'll be that kind of thing. And I'll award credit or not. That will be a binary. You get full credit or you don't get credit. So pay attention to those directions. But I think I've said this previously. If you engage with the poll questions, you don't have to worry about those discussions. You're welcome to look through them. But that's about it. Okay, so with that said, I'm going to go ahead and jump into, can I print out the word assignment? Oh, thank you for asking. So the word find and the crossword puzzle, I've added to the Canvas page. I think I have the directions on what I need. I need you to turn a PDF in. You can work directly in a PDF, or you can print it up, or you can download it, print it up, and then paste that in to a Word doc or a Google Doc file, and then export that as a PDF. I provided two links for how to do that. The important part is it has to be submitted as a PDF. So if you print it up, great. It just has to be printed, or it just has to be submitted as a PDF. If you haven't any sort of technical issues with that, let me know, and I can try to find out what software you have and what software solutions are out there. But it just has to be submitted as a PDF by 11 p.m. on the 26th. Okay. So let's jump into organic chemistry. Organic chemistry, and if you have any questions, I've got my chat window up here so I can look at that. So feel free to add them either as direct messages or group messages. Organic chemistry is defined as the chemistry of hydrocarbons and their derivatives. Of tens of millions of known chemical compounds, over 95% are compounds based on carbon. So organic chemistry, whenever you hear that, I don't want you to necessarily think organic, that means no pesticides. No, organic in this case, and the chemist perspective is that it's a carbon-based molecule or molecules that are largely carbon. Now, Carbon is an atom that can bond to other identical atoms to form long chains or rings. So, a common ring in biology, or a common carbon-based ring molecule in biology, looks like that. So, it's just a bunch of carbons, but then, what's also there is there's going to be hydrogen and hydrogen. I'm not going to draw all the hydrogens in, but there we go. That's a good example. Now, carbon will always make four bonds. Now, those four bonds can be a couple of different, I guess I like to say this word, permutations. They can be four single bonds. It can be two double bonds. There can be two single bonds and one double bond, and a single bond and a triple bond. So carbon will never have three double bonds because those double bonds, three doubles would end up being six total bonds, which is more than what carbon likes to do. So carbon likes to form four bonds, and how those are kind of distributed vary a little bit. There are, in addition to carbon and hydrogen, there are other atoms that are found in organic compounds. Some good examples, excuse me, are, and I've rearranged the periodic table. I grabbed some things from different parts of the periodic table. So if you look at this and you're thinking, oh, no, that doesn't look like what it does on the periodic table. You're absolutely right. So hydrocarbons are carbon and hydrogen-based molecules. There's also nitrogen, oxygen, sulfur, and then your halogens like fluorine, chlorine, and bromine. And that brings up actually our first poll question. So we've got 13:30 launch. Okay. Thinking about where fluorine is on the periodic table, and you might want to jump over to like a periodic table and say, how many total electrons does a fluorine atom have? This is thinking about our subatomic particles. And just so you guys know, one of the things that I like to do from time to time is I'll give roughly a minute for this question. But if 100% or if everyone in the Zoom answers the question, or if everyone who answers it gets it right, sometimes what I do is I'll say, oh, this one's worth a bonus. Sorry. A bonus point on an exam. Okay, so we're at about a minute and 10 seconds. I'm going to go ahead and stop the poll and share the results. So this was a little bit of a throwback, but I'll say that 63% of y'all got it right. So we were looking at fluorine on the periodic table. I'm going to stop my share of that and then just go back here. When we look at fluorine, the element and its symbol, there are a couple of numbers that were probably a little bit tempting. I think the most popular answer was 9, which is correct because 9 is the number of protons, and protons are positively charged. And if we're talking about an elemental atom, in this case, a fluorine atom, I don't say anything about the charge or anything like that. That means it's got the same number of protons and electrons. Now, one of the other popular answers was 10. And that's a pretty good answer because what fluorine likes to do is it likes to pick up an electron so it can complete its octet. Well, so I would say that 9 and 10 were the best two answers. The others were kind of decoys, 18 and 19. Well, 18.998 is the atomic mass of one atom of fluorine. So it's not the correct answer, but still a decent answer. Now, we can jump ahead. So if we look at a molecule like caffeine here, this is just an example of an organic molecule or an organic compound. We've got nitrogens and oxygens. And then what's kind of tough to see here, and this is just kind of the convention for um, drawing a organic molecule, is I'm going to circle a place on this molecule, and somebody add to the chat what atom is right there. What's in the red circle? And I'll give you a little bit of a hint. This is an organic molecule, and there is indeed an atom there. Carbon. You're absolutely right. So this is kind of the convention whenever people are drawing an organic molecule. Um, you kind of don't draw the carbons. Now, with that in mind, I want to show you this other example. Okay, so let's see. I'm going to start over here with our oxygen. We've got one, two. I'm filling in some of the things that I want you to get comfortable with seeing that they aren't there. Um, those lone pairs of electrons. Well, that would complete oxygen's octet because oxygen here has these two electrons, and then a double bond. So it's sharing four electrons. Now, what is kind of omitted in a couple of different places is hydrogens. Well, carbons are there. Hydrogens are really rarely, if ever, drawn. That's why earlier, whenever I was drawing this structure right here, sometimes what you'll see is something that looks just like this. I don't know why I drew it over those words. You'll see this right here. Nope, that's not drawn well. Let's try it again. There, 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 there. And that's a little better. That's a six carbon molecule. Does each one of those carbons have a complete octet? They do. How do they have that complete octet? Well, they have hydrogens bound to each one of those carbons. Okay. So that's just one thing that I want you to get a little bit comfortable with, that, carbons are going to be, like here or here or here. But like if we take this one in particular, what's not shown here is let's say that's a carbon. So we've got a single bond and a double bond. So that's a total of three bonds. What we do not draw here, and what conventionally is not drawn, is that hydrogen. Okay. Now, when it comes to bonding, electrons, first of all, they're not in the nucleus. Because what does your nucleus consist of? Protons and what other subatomic particle added to the chat? Neutrons. Absolutely right. So protons and neutrons are in the nucleus. Electrons, well, they're kind of spinning all over the place. Now, the all over the place is these orbitals. So it's possible that you've seen a model of an atom that looks like this. Here's my nucleus. You've maybe seen a model of an atom that looks like that, where these rings, these kind of oval-shaped rings, are where electrons kind of spin around. They're all over those places. Okay. Now, that's a simplified model for an atom. And these orbitals aren't really as accurate as they could be. But what I want you to know is that these orbitals all have different names. And I know in 1310, we talk a little bit about different blocks of the periodic table. We refer to the S block, the P block, the D block, and the F block. And if you're thinking, I don't remember that, understood. Okay. Because we're going to cut through and see what we really need to know about this. Now, think about these as basically the rings Around the nucleus where electrons are. ARE. Okay. Now, what's pretty complicated is whenever we have a bond formed between two atoms, um, the electrons between two bonds have to be in the same place. And what I mean by that is if I have an electron in one of my p orbitals and I want to share that electron with another atom, well, that other atom has to be able to accept an electron in its p orbital because I'm sharing a p orbital electron. Okay. Now, that gets kind of complicated and hairy. So, the solution and the explanation that has been devised over the years is that these orbitals hybridize. So, what that means is that an s orbital merges with a p orbital and with an f orbital. What these orbitals become is they become hybridized orbitals. So, that means that you can have an s orbital merge with a p orbital to make an sp hybrid orbital. You can have an s orbital merge with two p orbitals to make an sp2 hybrid orbital, or an sp3, which is an s orbital with three p orbitals. So whenever you see this sp3 or sp3d2, let's go with this sp3d2. What this is an s orbital plus a p plus a p plus a p plus a d plus a d. All of those things come together to make that sp3d2 orbital. Now, orbital hybridization is pretty darn abstract. What I want you to know, what you need to know, is the hybridization that carbon is capable of. Now, remember, carbon likes to form four bonds. Carbon can experience the following hybridization: sp, sp2, or sp3. Now, remember, an sp orbital is one s plus a p. An sp2 orbital is an s plus a p plus a p. Tell me what in the chat an sp3 hybrid orbital is made up of. Perfect. S plus P plus P plus P. Okay. It's I'm happy that you know kind of the makeup because that's a good question. I think that's a fair question. What are the orbital um what are the orbitals that come together to make an sp3 hybrid orbital? Now, a kind of next step for this is what does that mean? Well, what that means, and a kind of a simple way to think about it, and I think a very effective way to think about it is, well, this means that when carbon is a central atom, it can be hybridized, or it can, sorry, when carbon is a central atom, it's fair to ask the question, how many other things is it bound to? Is it bound to two things? Well, if so, then it's experiencing sp hybridization. Is it bound to three things? Well, then it's sp2. If it's bound to four things, then it's sp3. Now, what we're going to do is we're going to look at, on the next slide, this right here. Okay, we're going to go back to caffeine. Now, every single atom hybridizes orbitals. And if we look at something like this carbon right here, a question that I would ask on an exam would be, what is the hybridization of this carbon? And to answer that, the way that I approach this question is I say, how many things is it bound to? Well, I'm going to go up here. One, it's got the double bond going to the oxygen. Two, it's got a single bond going to the nitrogen. And three, we've got a single bond going to the hydrogen. So how many things is that carbon bound to? Three. Chris, you're absolutely right. It's sp2 hybridized. Okay. Now, next up is when we look at something like nitrogen. This is a little bit tricky. The question is, how many things does it like to go to? And now, what I need you to know is that you can see here's one, two, three. When you think about those, each one of those single bonds reflects two electrons. So that would be 6 electrons. Is that a complete octet? It's not. So nitrogen, one of the things about nitrogen is that nitrogen likes to also have a lone pair of electrons. So if we can go ahead and draw this in, 1 and 2. Now this lone pair of electrons is going to influence our result. So we'll go ahead and do a poll question on that one. Let's go ahead and answer that one, okay? Okay, so we got 30 people out of 33 answered. Our highest result was SP2, and you're right. So what we've got here, there are a couple of different answers. There's SP3, there's SP2, there's SP1 and SP. SP3D is also incorrect. So our best answer is going to be SP2 there. Okay. Now, next up, let's get into the kind of the dirt of organic compounds and organic chemistry as a whole. So here what we've got are hydrocarbons. Hydrocarbons are like I said previously, they're kind of the central part of organic chemistry. So whenever I think about, organic chemistry, I personally think about the oil and gas industry, and then I think about hydrocarbons, and I think about, you know, sorry, I think about motor oil, I think about octane. And if you think about octane ratings in gas, like some luxury vehicles require an octane rating of 93 or above. And that's just because it's a more pure form of gasoline. Okay, so terms related to hydrocarbons. We've got to have aliphatic compounds. Now, aliphatic compounds are typically going to be alkanes, alkenes, and alkynes. What's the difference between those three words? The suffix, ene or yne. Do you think that matters? Spoiler, it does. And we're going to talk about that. Next up in our big group of hydrocarbons are aromatic compounds. When you think about, does this word aromatic, does anyone notice anything about it? Does it trigger any sort of response to you? Add it to the chat if it does. Smell. Absolutely. Aroma. So aromatic compounds generally have an odor, something that you can detect. And with that in mind, I think it's important to understand that um, there's relevance to these compounds. There's relevance to your kind of everyday life. There's also halogenated hydrocarbons. Those are hydrocarbons that include, or sorry, those are hydrocarbons which also include halogens like fluorine, chlorine, bromine, iodine. Um, okay, so is this going to be on the recording or the? I believe that the PowerPoint's up. If it's not, I will post it. Yes. Um, no, the PowerPoint is up. It's also up as a PDF. And the recording, I will post that after I posted it to my YouTube channel. And then I'll post that link onto our Canvas page. Um, okay. Then what we've got, no worries, no worries. Um, Other groups of organic compounds, alcohols, phenols, ethers, esters, aldehydes, ketones, carboxylic acids, amines, amides, alkaloids, and many more. Now, with that in mind, are you going to have to memorize this list? No. Do you need to memorize this list? No. Is this list like a comprehensive list of every single type of organic compound? Nope. Are these just some examples? Yep. Are we going to dig deeper into some of these? Yep. Are we going to dig deeper into all of these? No. These terms will become a little bit more relevant whenever we're looking at those specific compounds and we're looking at, oh, this is an alkaloid, this is an amine. Um, and it's almost like the list will become kind of second nature to you. I'd rather you understand what a specific aldehyde is than know that something is an aldehyde. But like I said, as we look at those specific aldehydes, you're going to be like, oh, yeah, that's an aldehyde. I know that because of X. Okay. Now, many organic compounds, and this is really important for understanding organic compounds, are multiple things. For example, a compound can be classified as an alcohol and an aliphatic compound. That's important to know just because of the fact that, or that's important to know and relevant to why I'm not asking you to memorize this list or the list of different types of organic compounds. Just because you're going to look at some and be like, oh, well, this is a aliphatic compound. Oh, okay, cool. This is also an alcohol. Oh, I see that. So that's why I like to throw the terminology at you, but then we'll get into the dirt of why some things are relevant and matter. Now, next up is hydrocarbons. Digging deeper into hydrocarbons. That's where we're going to go first. They can have single or double bonds. They can also even have triple bonds. Primarily, though, they're going to have single bonds and double bonds, just because triple bonds have a tendency to limit the kind of complexity of the molecule. Aliphatics are compounds that can have straight chains, branches, or can have rings. This is where it gets complicated and where it's kind of like a square is a rectangle, but a rectangle is not a square. Not all ring structures are aliphatics, and the reason is that some of these ring structures are aromatics. Now, nomenclature is a really important part about part of organic chemistry. In chemical nomenclature, specifically in organic chemistry, in addition to classifying compounds, we are very interested in prefixes and suffixes. Prefixes give you a sense of the complexity of a molecule, and the suffix is also going to tell you something about that molecule. Now, this is true for every organic compound, but we kind of have a narrow scope right now, and we're looking at our aliphatics. Below in this box are some aliphatic compounds. We've got methane, propane, cyclohexane, and ethanol. Underneath that, we have two other aliphatic compounds. We have alkene and alkyne. In this block to the right, we've got some aromatics. Benzene, ethylbenzene, naphthalene. Does anyone know what naphthalene is used for? I'm like 98% sure. I was going to say 99, but I dropped it down to 98%. I think naphthalene hair removal, maybe, but I think it's also in mothballs. So if you ever have like an elderly person who's saving something, I believe that the mothballs are they have naphthalene because what it does is it's an aromatic compound, so it diffuses and it has an odor, and that odor is a repellent to moths. I'm about 98% sure on that. Now, one of the things about these aromatic compounds is they've got some double bonds. Now, what's significant about these double bonds is that they are kind of like every other bond is a double bond. So they're you're never going to have two consecutive double bonds. It's basically going to be every other bond is a double bond. So anytime you see that, I want you to think aromatic. That that compound probably has an odor. Now, what I want you to look at over here, I'm going to bring up this. Looking over on the left, we've got alkene and alkyne. And I'll take it back just a minute. Um, Alkene here is an example. This is an example of an alkene. And this is also an example of an alkyne. Now, let's go ahead and see that ENE and YNE and answer this question. And look at those aromatics. What do those all end with? Okay, we got about 10 seconds left. Two more people to answer. One more person. If we can do it, we get a bonus point on the first exam. 4, 3, 2, 1. Close. Close. We got 32 out of 33 people who answered, and 75% of you guys said that molecule, when you see ENE, that molecule has at least one double bond. You're absolutely right. This is an example of an alkene. This is an example of an alkyne. Benzene. Well, how many double bonds does it have? It has three. Ethylbenzene has three. Naphthalene has five. An alkene, that suffix, when you see that ENE, think it's got at least one double bond. It might have two, it might have five, it might have 50, but it's got at least one double bond. So that's when you think about suffixes, think about ENE and YNE. What do you think YNE means in terms of bonding? Go ahead and add to the chat your response to that or your thoughts on that. This is for YNE. We've got alkyne. There's a triple bond present. So if it has, well, it could have three triple bonds, but a triple bond must be present in an alkyne. When you see ANE, that molecule has nothing but single bonds. When you see ANE, so think about it almost like a progression. ANE, ENE, YNE. ANE, single bonds. ENE, double bonds. YNE, triple bonds. Okay, so then we've done that. Now, I'd like you to think back now with respect to prefixes. You were once in elementary school, and you learned what a hexagon was. And so, with that in mind, You could also think about if you like Ultimate Fighting. Think about the progression of shapes and numbers of sides. We got 40 seconds for 19 people to answer this. 13 people left. 10, 9. If we get every person to answer this, there's a bonus point on the first exam. We got 6 people left in 20 seconds. Okay, 4, 3, and 15 seconds. We got 3 people who need to wake up. Or 10 seconds. Or make that decision. Sometimes taking a risk. 3 seconds. 2, 1, donezo. Okay, the correct answer is 9, and the majority of you answered that. 63% of you said 9. You're correct. A nonagon has 9 sides. So that prefix for shapes is relevant to prefixes for organic compounds. There are some that are similar, but then there's some that are a little bit different. So pentagon, hexagon, heptagon, octagon, nonagon, decagon. So basically the first 4 prefixes are the ones that you got to sort out. Meth indicates that that molecule has 1 carbon. Eth has 2 carbons. 3 is prop. 4 is bute. So examples of this would be butane. Propine. What can you say about propine? Well, one thing that you can say is it has 3 carbons and it's got a triple bond. Now, if we look down, and so then here what we've got, this molecule right here is ethene. 2 carbons and a double bond. This compound right here, 2-decanone. That's introducing another term. ONE, that ONE suffix. Well, that ONE suffix has to do with the presence of this oxygen. Does anyone want to take a wild guess in the chat what carbon number that oxygen is found on? I got it. Vote for what? Okay, so Chris, you're absolutely right. It's on the 2nd carbon, hence 2-decanone. The DEC indicates that it has 10 carbons. The 2 indicates that, well, that oxygen is found on carbon number 2. Okay, now let's keep going through this. So here are what we've got. What is the suffix of the first 2 here? Well, we've got meth and prop. Now take a look at that 3rd compound. What do you know about it? Are there different prefixes for other elements beside carbon? No, because that's a fantastic question. The way that we name organic compounds, we're centered around carbon. So we care about, well, how many carbons are in that chain? If there's another element like fluorine or something, we would say 5-fluoro octanol, in which case we would be giving some more information about that fluorine, because fluorine, yeah, it's found in organic compounds, but it's not the centerpiece. The centerpiece of an organic compound is definitely going to be that carbon. That's a fantastic question. Did I answer that properly? Okay, cool. So whenever we think about organic chemistry, think about carbon, 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 carbon. That's our first thing. And then we'll go on from there. Now, when we look at these compounds, the suffix ane means a compound in question does not have double bonds. Another term for this is to say that these molecules are saturated. So if something has no double bonds, it is considered a saturated molecule. Now use the prefixes that we previously saw along to name the compounds on the next page. Okay, so the first 3 up top, this gray ball is our carbon, the rest are hydrogen. So methane. Ethane, and then let's see, one, two, three. That's propane. And now we're ready for poll question. Either 100% answer it correctly or every single person responds gets us a bonus point. Right now, oh, never mind. So now what we need to do is get every single person to respond. 15 people left. We got 30 seconds. I'll tell you, the correct answer is butane. The second answer that people put down was alkane. Alkane is how this molecule can be classified because, well, it is an example of an alkane. There's no double bonds. Propane is incorrect because this molecule has 4 carbons. So 4 carbons, that's what we need to count up. 1, 2, 3, 4. It is bute. And then since it is a alkane, that's where we add ANE. Okay, we only classify on Lewis structures. Okay, that's a great question, and we're absolutely going to classify on Lewis structures, but whenever the question is asking about what is the specific name of this, then you have that common name. And so you would say, well, this is butane. I could ask the question, how is this compound classified? In which case, I could give you alkane, alkene, butane. Well, butane is an answer that's a little bit of a decoy because if I was asking about the classification of it, then I wouldn't put butane because that's the common name. That's kind of like saying, I am a human being. And then if someone were to say, how would you classify me? And you said, I would classify him as Joel. Well, that's not the best answer. The best answer would be, well, he's a human being, as opposed to a I don't know, a giraffe. Does that help? I hope that it does. Okay, cool. It gets a little bit murky and sometimes it kind of goes back and forth, it feels. Okay, so we've got prefixes and suffixes. Prefixes, I want you to know these stems. Meth through dec, 1 to 10. Then we've got the suffix ane, ene, and yne. That's our focus so far. When you see ene, you've got at least 1 double bond. When you see yne, you've got at least 1 triple bond. And when you see ane, you have no double or triple bonds. That's a great question. ONE is for that 2-decanone. That is dealing with what's known as a functional group, and we're going to tackle those next class, or on Monday, we're going to tackle those. Just because those kind of like ONE is related to oxygen and where it is. We'll get to those on whatever, yeah, Monday. We're just kind of putting our foot into organic chemistry. Monday, we're gonna, put both feet and maybe stand in the water up to our knees. So don't worry about ONE right now. Okay. Now, what is the significance of this? Here is a list of, well, tons of different organic compounds. Okay, we've got, well, methane all the way up to icosane. Icosane has 20 carbons. It's got a formula that is, well, 20 carbons, 42 hydrogens. Methane, well, CH4. All the way through all of these are all alkanes. Not a single one has a double bond. Now, one of the things that's important to know about these compounds is that their melting point varies. Methane has a melting point of 100, negative 183 degrees Celsius. So if you were to walk outside and someone said, "Oh, look, there's some methane," that'd be really tough because you'd be like, and you maybe even had some experience with this, but um, that's going to be a gas. So if someone was like, "Look, there's methane," then they're probably pointing to either a container or I don't know what they're pointing to. Um, Now, next up is as we kind of go down this list, our melting point, well, it increases. So that's a trend that's important to know. As the number of carbons goes up, the melting point also goes up. Your boiling point, well, same thing. As the melting point increases, or sorry, as the number of carbons increases, the boiling point increases. Then, last but not least, the density of these. So this is the density at 20 degrees Celsius. How many grams per milliliter? Well, the first four, they're going to be a gas at 20 degrees Celsius. Butane is something that people have a little bit more experience with because if you've ever used like a, a Zippo lighter, well, that has butane in it. Now, the density of the density of gases increases as the number of carbons increases. There's almost basically everything increases as the number of carbons increase. Okay, so what we know about our aliphatic compounds, just as a little bit of a review, we've got our prefixes, our suffixes, and then these physical properties, melting point and boiling point, and the states all trend towards kind of more stability. Melting point and boiling point go up as carbon number goes up. Density also goes up until it reaches a solid. Now, as I mentioned previously, aliphatics are compounds that can be straight chains, they can be branched, or they can have rings, though not all ring structures are aliphatics because many ring structures are aromatics. Now, this word right here, branched, this is super important because if we wanted to name this molecule, what we would do is we would look at this formula. And this, you maybe are not familiar with this, but basically an end to a line indicates a carbon. So I'm going to draw this molecule, but I'm going to draw it with all the carbons and hydrogens. So C, C, and I'm going to draw them right next to each other so that you can kind of get a better picture for that. And I'm going to draw CH3, CH3. Here's an H coming down here, H on top, H below. And if you look at those last three hydrogens that I drew, one of them I drew with a line going to it, and the others I didn't. What's the significance of that? That's really just artist preference. So that's just how I would do it. I could just as easily erase that and write this right here. Um, H, H, and then I'm going to do H3 here. Okay. So the molecule that I just drew in red is the same as this molecule that's already depicted in black. Okay. Now, whenever we're drawing a molecule, or whenever we're trying to come up with a name for a molecule, simply thinking about the number of carbons of this molecule right here, we would say 1, 2, 3, 4, 5, and 6 carbons. Okay, so 6 carbons. What if I told you that this was not hexane? I know you're probably too shocked to even respond on your chat. You're probably just like, I don't believe this. I refuse to believe this. I hope that nobody's thrown their laptops out their window or broken their keyboards in two or anything of that nature. I should have warned you before I shared this information with you. I'm sorry. I'm sorry. But this is not hexane. This is, in fact, pentane. And the reason that this is pentane is because of the rules that we follow when it comes to Stanley, I will. I will. This is too much of a shock. I hope that everyone's doing all right. Um, if you need to, if you need to take a breather, step outside for a little bit, I respect that. Be strong. Be strong, everyone. I know you can do it. Okay. This is pentane. When we're naming compounds, what we do is we find the longest possible chain. So, yeah, this has 6 carbons, but to use that prefix, we've got to find the longest possible chain. The longest possible chain in this molecule is 5 carbons. And I know that this is a potentially a controversial subject. So this is my warning. Some of y'all might have numbered it like this: 1, 2, 3, 4, 5. There might be somebody in this class who said, aha, I didn't number it like that. I numbered it like this: 1, 2, 3, 4, 5. And here's the controversy. Is one right and the other's wrong? No, no. They both identify a 5 carbon chain. That's what we're looking for. Okay, so then a fair question is, how do we account for that other carbon? Well, that's where we come up with a little bit of a kind of workaround for this. Okay, so here are the steps for naming an organic compound. Identify the parent chain, the longest chain, the longest carbon-based chain. We've done that. Number the chain. Okay, we did that. We mixed that in. And then name the substituents. What on earth does that mean? Well, a substituent is kind of a branch or a modification to it. In which case, this, I'm going to go with this numbering: 1, 2, 3, 4, and 5. That's your substituent. Okay, so we've got a substituent. And then what we've got to do is we've got to name it. This right here is CH3. When we find a compound that has 1 carbon, that's a methyl, like methane. So we name that substituent methyl. Okay. So based on that, we've got kind of a molecule that, as we're putting this name together, we've got methyl pentane. That's right. Now we have to assign a number to that substituent. So we have to kind of give definition of where that is. We would say, okay, well, assign a number. The way that I numbered it right here, well, it's going to be at carbon number 2. Well, what if somebody actually went totally rogue and they did this? 1, 2, 3, 4, 5. Is that person right? Is the person who drew in purple correct? No. Alex, that's absolutely right. Because this is the substituent. I'm going to write substituent. I shouldn't have used, dang it. Here, I'm going to change to white. Substituent. Look at that. That's artistic right there. So this is our substituent. That substituent is 1 carbon. That is a methyl group. So, okay. So the question is, well, when we look at this option down here, we've got our branch. Is it at 2 or 4? The answer is it's at 2. And that is the correct name, or that is the correct way of doing it. The reason for that is because you want to give your substituent the lowest possible number. So this is 2-methyl propane. Our main chain, Joel, methylpentane. There we go. Our main chain is 5 carbons long. We have one substituent. It is a methyl group. It is CH3. Where is it? Well, it's at carbon number 2. I'm going to erase the carbon numbering that is incorrect. Now, a fair question for this would be, well, what if I numbered from here if I said this was 1? Well, this is still a methyl group. It's still going to be 2-methylpentane. Okay. Now, those substituents can get longer. Yeah, sure. So, why we start numbering at 1? Um, top one. Those, Andrea, that's a fantastic question. And this, it actually doesn't matter where you start. You just have to start either here or here. And the reason for that is because, well, where is our the question is really where is our methyl group? Where is our branch? And we want to give our branch the lowest possible number. So I'm going to erase, oh, let's draw. I'm going to erase all this. So if I started from the far left, that'd be 1, 2, 3, 4, 5, and then here's our methyl, we'll say. So this would be 4-methyl pentane. Okay. Well, an alternative to that would be, we're going to start on the far right. 1, 2, 3, 4, 5. Well, this would be our methyl. So we've got basically 2 possible names, 4-methylpentane or 2-methylpentane. And then the question is, which one's right? Is it 2-methylpentane or 4-methylpentane? Well, the answer is it's 2-methylpentane. Because what we're trying to do is give that methyl group or any substituent the lowest possible number. That's our objective. And if I instead started rather from, if I started right here, this is still methyl and it's still 2-methyl. Does that help? Awesome. This gets complicated and it gets tricky, but it's, first of all, the complexity of the questions that we're going to have in this class are not the same that you would see if you took organic chemistry for 2 semesters. Because names can get super complicated, but we're not going to do that. Now, just as this is 2-methyl, those branches can be longer. If a branch is 2 carbons, it's going to be an ethyl group. If it's 3 carbons, it's propyl. If it's 4 carbons, it's butyl. So that's really what you have to think about. Now, let's look at these 2 compounds. I'm going to start on the left here. 1, 2, 3, 4, 5, 6, 7, 8. So add to the chat what you got for this compound's name. Two-methyl octane. You're absolutely right. We've got octane because there's nothing but single bonds. And then we have a methyl group up here. Where is that methyl group? That's found at position number 2. Great job. Okay. Now let's go to our next compound. This one, I like this sort of question as a practice or a quiz question because of the fact that, well, we can start a couple of different places. Start here. 1, 2, 3, 4, 5, 6. Okay. Now I'm going to switch colors so I can start from another place. Start up here. 1, 2, 3, 4, 5, 6. Okay. Then one last spot that I'm going to start is going to be right here. 1, 2, 3, 4, 5. Okay. One thing that I think we can all agree on is the last numbering is out. And we can discount that numbering because of the fact that what's the length of our chain? 5 carbons. What's the length of our chain with our other numbering schemes? 6 carbons. So I'm going to go ahead and erase that right there. Let me know if that's confusing as to why we did not do that one. Okay. So now we've got these red versus green. Okay. If we use the red numbering, where we start from the left-hand side, um, we get hexane because it's 6 carbons. So we've got hexane. I think everyone's probably on board with that. But then let's see, I'm gonna go with red and then green. Both of them end with hexane. Now, where it gets a little bit complicated is we've got, this is a methyl. This is also a methyl. 3-ethyl hexane. Alex, that's a great proposal. And this is one of the places where it gets complicated. Okay, the reason that this is not ethyl hexane is because think about think about that 6 carbon chain as being like, well, we've got something on the right hand side and on the left hand side. The thing on the left hand side, or I'll just say the thing on the top right here, is a methyl group. And then the thing on the bottom is a methyl group. We don't have an ethyl group there because these 2 carbons, this one and this one, are not in a chain stemming from the same place. So the way that we label this would be 3, 3 dimethyl because we have 2 methyl groups. The alternative to this, does that make sense, Alex? I understand. And I got to be completely honest with you, that's what I expected your response to be. I apologize. On behalf of science and organic chemists, I apologize. So, with that said, when it comes time for your exam, don't expect like 30 questions just like that. There's going to be some questions that are like low-hanging fruit questions, and then I don't even think that I'd go with something like that. Just this to me is like a good let's talk about it sort of problem-solving question. And thank you very much for your honesty. I appreciate it. So the alternative with the green, I'll get to that in just a second, Javion. This would be 4 dimethyl hexane. And, it's 3 just because it has lower numbers. Okay, Javion, that's a fantastic question. What would ethyl hexane look like? Okay, so ethyl hexane, an ethyl group that's kind of the terminology, ethyl group or a methyl group or a butyl group. Ethyl hexane, let's just go with 3-ethyl hexane looks like this. I'm going to draw something very similar. basically the same backbone. And then that right there. So 1, 2, 3, 4, 5, 6. There's our 6 carbons. And then 3 ethyl hexane. Looks like that. So on carbon number 3, that's where we have our 2 carbons that make up that ethyl group. And then, absolutely, this is where it can also get kind of complicated because you could have there and then here. Actually, I'm going to leave that one off. I'm going to leave that one off. This right here would be, okay, let me think. If I, 3, 3, ethyl, no, it's, no. Let me fix that. Methyl, we've got our methyl group right here. Ethyl hexane. And then it could get complicated because it's also, we had it right here, 2, actually, yeah, 2 methyl, 3 methyl ethyl hexane. This is where it can get kind of hairy and complicated. So thank you very much for bearing with me on this. I want you guys to know the fundamentals of find the chain, what's the substituent. Your substituents are generally going to be methyl, ethyl, butyl, or propyl, and then go from there. Identify basically what's the best name for this compound. Now, our next group of compounds are our alkenes. That means that we've got that stem, 1 through 10, the meth through dec, and then ENE indicates that there's one double bond. Okay. Over here on the right-hand side, we've got the molecule ethene. Ethene, 2 carbons. ENE means that there's one double bond. Where could that double bond possibly be? It has to be between our 2 carbons. Now, the carbons with a double bond are unsaturated. That term unsaturated means they have a double bond. Okay. Now, a fair question when it comes to alkenes and that stem is, can methene? No, it cannot. Methene cannot exist because an alkene is defined by a double bond between 2 carbon atoms. Well, if you only have 1 carbon, you can't possibly have a double bond between, well, 2 carbons. There simply aren't enough carbons. So methyl groups only have 1 carbon and thus can never have a double bond to carbon. Alkynes. Alkynes have that same stem, but with a triple bond. Ethyne. Well, 2 carbons and a triple bond. Hydrogen and hydrogen. Ethyne is something that you've maybe heard of, but you've probably heard of it as acetylene, an acetylene torch. And then we've got here 2 butyne. Well, how many carbons does butyne have? But, 4. 4 carbons. So butyne, 2, 3, 4. Triple bond right here. 2 butyne. Numbering from the left, 1, 2, 3, 4. Numbering from the right, 1, 2, 3, 4. So that's how we have 2 butyne, and this is how we have 1 butyne. Alkynes are also unsaturated. So when you hear the term saturated, think nothing but single bonds. Unsaturated means at least one double bond or possibly a triple bond. Now, cyclic hydrocarbons, or cyclic HC as I've decided to name them, well, can you name, let's go with this one right here, the one that I circled. Add to the chat the name of that molecule. Cyclohexane. It's cyclic, cyclo, then you add the stem, hex, and then you add the ANE. Perfect. Cyclohexane. Okay. The one on the far right here. Well, it's cyclic, so cyclo. And then we've got 1, 2, 3, 4, 5, 6, 7, 8. Cyclooctane. Chris, fix one little thing about that. And ignore my numbering. We've got a 1, 2, 3, a triple bond there. So when we have a triple bond, what is the suffix that we need to use? Perfect. Perfect. Great job. Great job. So this is cyclooctine. It feels silly to say that. What's really important, though, to know about this is, and well, if you've ever been to a wedding, there's always the moment when someone says something like, I'll give you this ring because a ring is a metaphor for our relationship. It has no beginning and it has no end. Yeah, exactly. Okay. Do we number when there's only one triple bond or one double bond? No, because this isn't this isn't carbon number one, and this isn't carbon number one. So you wouldn't say like one cyclooctine. You would just say cyclooctine. If there's multiple, then you would make some modifications to it. But this is cyclooctine. We've got cyclopentane, cyclohexene, cyclopropane, cyclohexane, cyclobutane, cyclooctine. Okay. Well, that's what I got. Your assignments are up, your quizzes are up. Sunday night at 11 p.m. I've got office hours that start in about 17 minutes. Um, Thank you guys so much for coming to class, and thank you for asking really great questions and giving good responses. I really appreciate it. I'm going to go ahead and stop my recording.